Okay, in the last couple of lectures, we have discussed the Laplace transform, especially unilateral Laplace transform. That is, the unilateral Laplace transform x of s is defined as the limit is from 0 minus to infinity x of t e to the minus st times dt. The inverse Laplace transform is 1 over 2 pi j integral of sigma minus j infinity to sigma plus j infinity x of j omega e to the st and ds. Okay, now in this lecture let us talk about bilateral Laplace transform. Okay, so let us start from the basics, that consider a linear time invariant system. Okay, with the input is del of t and the corresponding output we call them h of t. Okay, now in case instead of del of t, you apply some arbitrary signal x of t to the same system, LTA system, then the output is y of t. Now what is y of t? This y of t we said x of t convolved with the h of t, right? Now instead of like x of t some arbitrary signal, if it is something called complex exponential signal, let's say e to the st, then your y of t is equal to h of s times e to the st. Please recall this property, this we already discussed. Okay, and we said h of s is the system function. So this relation is hold true only if x of t is an complex exponential signal. Otherwise we cannot hold this relation. This relation is not true. Okay, so it is true only, please remember that. Now what is h of s? H of s we got as integral of minus infinity to plus infinity h of t e to the minus st times dt. Okay, now here s is sigma plus j omega. If you assume sigma is equal to 0, then s becomes j omega. Therefore in the above equation it becomes h of j omega is equal to this equation, h of t e to the minus j omega t times dt, and this corresponds to what? Fourier transform of h of t. Fourier transform of h of t. Therefore for general values of the complex variable s, it is referred to as the Laplace transform of the input. Okay, so Laplace transform of the input, this function. Okay, what is that function? Impulse response function. Okay, now therefore the Laplace transform of a general signal x of t is defined as x of s is equal to integral of minus infinity to plus infinity x of t e to the minus st times dt. Now this is called a bilateral Laplace transform. Okay, okay, so this bilateral Laplace transform involves an integration from minus infinity to plus infinity. We have discussed unilateral Laplace transform. In that the integration involves 0 minus to infinity x of t e to the minus st dt. This is unilateral Laplace transform. Okay, so in the unilateral Laplace transform, the limits of integration from 0 minus to infinity. So that is the only difference. So here you are considering the in bilateral Laplace transform, you are considering the signal from minus infinity to plus infinity, and in this case you are assuming x of t is equal to 0 for t less than 0. That's it. And as I said, for bilateral Laplace transform also, the time domain and s domain is denoted by like this: x of t, you put a arrow mark like this, and the reverse you put a arrow mark like that. So this is a Laplace transform pair, the relationship between x of t and x of s. Okay, if you put s equal to j omega in this expression, then it becomes x of j omega is equal to minus infinity to plus infinity x of t e to the minus j omega t and dt. And don't you see, this is precisely the definition of what? Fourier transform of x of t. Okay, therefore your Laplace transform x of s is nothing but, you put s is equal to j omega in the Laplace transform, that becomes the Fourier transform of x of t. Sorry. Okay, so the Laplace transform also bears a straightforward relationship to the Fourier transform when the complex variable s is not purely imaginary. So if sigma is not equal to 0, then s becomes sigma plus j omega. Therefore x of s becomes x of sigma plus j omega. This is equal to integral of minus infinity to plus infinity x of t e to the minus st. No, s becomes sigma plus j omega times t and dt, right? So if you rearrange this, then x of t times e to the minus sigma t times e to the minus j omega t and dt. Okay, you put like this, then you can recognize that this is as a signal, and this one is the Fourier transform of x of t multiplied by e to the minus sigma t. Therefore the Laplace transform of x of t can be interpreted as the Fourier transform of x of t after multiplication by a real exponential signal. Therefore Laplace transform of x of t is equal to Fourier transform of x of t after multiplication by a real exponential e to the minus sigma t. Okay, so the real exponential e to the minus sigma t may be decaying or growing in time depending on whether sigma is positive or negative. If sigma is positive, then e to the minus sigma t is decaying. If sigma is negative, then e to the minus sigma t is growing in time. Now let us consider an example. X of t is equal to e to the minus at times u of t. Now by definition, x of j omega bilateral Laplace transform is minus infinity to plus infinity x of t e to the minus st and dt. I'm sorry, this is, let us find out a Fourier transform first. This already we did. Okay, so if we substitute, then it becomes 0 to infinity e to the minus at times e to the minus j omega t and dt, and this answer is going to be 1 by a plus j omega, and the assumption is a greater than 0. Similarly, the Laplace transform is x of s is equal to sigma integral of minus infinity to plus infinity x of t e to the minus st times dt. So now the signal exists from 0 to infinity because we have the multiplication factor here u of t. So 0 to infinity e power minus at times e to the minus ast times dt. So this is e to the minus of s plus a times t and dt. I'm sorry, 0 to infinity. Okay, now what is the answer for this? 1 divided by s plus a. Okay, or else you do one thing, you put s equal to j omega in this, then integral of maybe I'll write down here 0 to infinity e to the minus sigma plus j omega plus a times t and dt. Okay, and this you can write it as 0 to infinity e to the minus sigma plus a times t times e to the minus j omega t and dt. Now if you evaluate this, then it will be 1 divided by sigma plus a plus j omega, right? So therefore the answer is 1 divided by sigma plus a plus j omega. Now here what did we say? This real part should be greater than 0, right? Should be positive. Similarly here this real part also must be positive. That means what? Sigma plus a must be greater than 0. Or equivalently we can say that s is equal to sigma plus j omega, then you can write this expression as real of s must be greater than sigma. Sorry, must be greater than minus a, because if the a goes to the right hand side, then it becomes minus a, right? So minus a, then sigma and j omega if we combine, then it becomes s plus a. Therefore e to the minus at times u of t, if we take Laplace transform, bilateral Laplace transform, then its Fourier Laplace transform will be s plus a, and real of s must be greater than minus a. Okay, for example, if a equals to 0, then what will happen? Then e power 0 times u of t, which is u of t, then the corresponding Laplace transform in the right hand side, this becomes, put a equal to 0 in this side, then s plus 0, which is 1 over s. Okay, and here what is your convergence? I mean the real of s must be greater than this value. So this value we assumed 0, therefore 0 here. Therefore u of t, if you take Laplace transform, then it becomes 1 over s, and real of s must be greater than 0. Okay, and we already said that the Fourier transform does not converge for all signals, but the Laplace transform may converge for some values of real of s and not for others. Okay, so that's what we said. If you take e to the 2t times u of t, no Fourier transform, but this guy has Laplace transform for some values of real of s, that we will see. Okay. Now let me take one more example. X of t is equal to minus e power minus at u of minus t. Okay. So the previous example was e to the at times u of t, e to the minus at u of t, and now we are considering minus e power minus at times u of minus t. That means your signal will be in the negative direction. Okay, when t equals 0, then it will be minus 1, and then your signal goes like this. This is your minus e power minus at times u of minus t. So in this case, what is your Laplace transform? X of s is going to be, the signal exists from minus infinity to 0. From 0 onwards, it is 0. The signal value is 0. So integral of minus infinity to plus infinity x of t e to the minus st times dt. So minus infinity to 0 minus e power minus at, then u of minus t e to the minus st and dt. Now in this range from minus infinity to 1, this guy is equal to 1. Therefore minus integral of minus infinity to 0 e power minus at times e to the minus st dt. So minus infinity to 0 e to the minus of a plus s times t and dt. Okay, now minus of e to the minus of a plus s divided by minus of a plus s, or s plus a, you can write either way, and the limit is minus infinity to 0. Now what is the upper limit? This minus and that minus will get cancelled. So 1 divided by s plus a, then e to the s plus a times 0 minus e to the minus s plus a times minus infinity. Okay, now we need to think a little while for this. So 1 divided by s plus a, this is 1 minus e to the minus of s plus a times minus infinity. So here I have one minus sign and here I have one minus sign. Both the guys will become plus. So I have e to the s plus a times infinity. Now what happens in the exponent? We have s plus a times infinity. If s plus a is positive and infinity also already positive, so positive times positive, it is positive. Therefore what will happen? E power infinity, so it becomes infinity. Therefore if s plus a is greater than 0, that is positive, then the integration will not converge. Okay, it leads to an infinite value. So in that case, then if s plus a is negative, then negative times plus infinity is going to be minus infinity, right? Therefore e power minus infinity is equal to 0, so it converges. Therefore in order to find the Laplace transform of this signal, which one? This e power minus at u of minus t, for this signal, this guy should be less than 0. This exponent s plus a must be less than 0. That is, s plus a must be less than 0. As I already told you, we least bother about the imaginary part. We only concentrate on the real part. Therefore, real of, maybe I'll write down here. Let me finish this first. So 1 over s plus a, 1 minus 0. This 0 occurs only if real of s plus a is negative, less than 0. Negative means less than 0. Therefore the final answer is 1 divided by s plus a. Then real of s plus a is less than 0. That means real of s plus real of a must be less than 0. That means what? Real of s is less than minus real of a. Real of s is sigma, right? Therefore, sigma must be less than minus a. So, the final answer is e power minus at u of minus t minus is going to be again the same relation 1 plus s plus a, but this sigma must be less than minus a. Laplace transform. If you recall the previous example, and here also you got 1 divided by s plus a, but here it is greater than minus a. Okay, so this is the only difference. So if we take e power minus at times u of t, then its Laplace transform also same expression 1 over s plus a, but here sigma is greater than minus a. Okay, if you compare let us say equation 2 and this is equation number 1, the algebraic expression for the Laplace transform is identical for both of the signals. For e power minus at times u of t minus e power minus e to the minus at times u of t, both have the same Laplace transform. However, for the same equations, we also see that the set of values of s for which the expression is valid is very different in the two examples. Here the expression converges for sigma less than a, and here it converges when sigma is greater than minus a. Therefore, specifying the Laplace transform of a signal, both the algebraic expression and range of values of s for which this expression is valid are required. If you simply give the Laplace transform, that is not enough. You need to provide at what range the expression will converge. And this is called region of convergence, as I said. ROC means region of convergence. That is, ROC consists of those values of s, sigma plus j omega, for which the Fourier transform of x of t times e to the minus j omega t, x of t times e to the minus sigma t converges. Okay, so how do you represent this ROC? You take this guy. This is sigma and this is omega, I mean real of s, and this one is imaginary of s. Okay, now you put a point minus a somewhere else. This is minus a. Your region of convergence will be like this towards the right hand side. Okay, so here real of s is greater than minus a. So this is a signal corresponding to e to the minus at times u of t. On the other hand, if you take minus e power minus at times u of minus t, then this is minus a. So the region of convergence left of this minus a. Okay, so here real of s is less than minus a. That's it. Therefore, this is a convenient way of representing the region of convergence through some graphical procedure. Okay, and this type of plane is generally called S plane, associated with the complex number s is equal to sigma plus j omega. The coordinate axes are real of s and imaginary of s. Okay, the horizontal and vertical axes are sometimes referred to as the sigma axis and j omega axis respectively. Okay, the shaded region, this region represents the set of points in the S plane corresponding to the region of the convergence. Okay, so this is the region where your Laplace transform exists. For your signal, minus e power minus at u of minus ut, and this is a region where entire your right side of your point s equal to minus sigma equal to minus a, where your function e to the minus at u of t converges. Okay, now let me consider one more example. X of t is equal to 3 times e to the minus t u of t, let's say minus 2 times e to the minus t u of t. Okay, now you find the Laplace transform of this. X of s is equal to integral of minus infinity to plus infinity 3 times e to the minus 2t u of t minus 2 times e to the minus t u of t, multiply this whole thing by e to the minus st dt. Okay, now you break this into two integrals, 3 times e to the minus 2t u of t dt minus 2 times integral of it, you can put 3 here, no problem, t, I'm sorry I forgot one value, e to the minus st dt minus 2 times integral of e to the minus t u of t, then e to the minus st times dt, and the limit is minus infinity to plus infinity, but your signal is multiplied by u of t. U of t is equal to 1 provided that your t lies between 0 and infinity. Okay, therefore this integral becomes 3 times integral of 0 to infinity e to the minus t e to the minus st and dt minus 2 times integral of 0 to infinity e to the minus t e to the minus st and dt. Okay, this one is we already calculated. If you have e to the minus at, then its Laplace transform is 1 over s plus a. So here also 3 times, instead of a I have 2 here, right? So therefore 1 divided by s plus 2, that's all. And here what is the a value? A value is equal to 1, therefore minus 2 divided by s plus 1. Straight away in one shot you can write down the result. No need to find the integration and substitute the limits and all. Simply you can write down. Once you know this formula, e to the minus at has Fourier transform, Laplace transform 1 by s plus a. Okay, now individually if you look at e to the minus 2t u of t, then it has a Laplace transform divided by s plus 2, and then we saw that real of s must be greater than minus 2, and then e to the minus t u of t, then the Laplace transform is s plus 1, and real of s must be greater than minus 1. Now the set of values of real real of s for which the Laplace transform converges, okay, both term converges, real of s greater than minus 1, because see you have two region of convergence. One is this one, real of s is greater than minus 1, and another one is minus 2, like this. So what will happen if you take let's say minus 2. If you consider this condition for the whole, see individually for e to the minus at u of t, this is a region of convergence. Individually for e to the minus t u of t, this is a region of convergence. But if you combine these two guys together, then if you consider this value, then this will not converge. Okay, so either you should take this or this. For for the sake of argument, let us say your region of s is greater than minus 2. Okay, in that case what will happen? E to the minus t, e to the minus st and dt, and the integral is 0 to infinity, right? So e to the minus t e to the minus of sigma plus j omega. Okay, sigma plus j omega, then what you do is you take a j omega into t integral 0 to infinity e to the minus of 1 plus sigma times t times e to the minus j omega t and dt. Okay, now if we substitute as per the condition, we assume that real of s is greater than minus 2. Let us take 1.5 minus 1.5. So in that case, what will happen? See, this minus 1.5 is greater than minus 2, right? Correct. Therefore, for the sake of argument, let us say sigma is equal to minus 1.5. Then in the exponent, what do you have? Here e power minus of 1 minus 1.5 times t. Now this becomes e to the minus 0.5 times t. Minus into minus, it becomes plus. So e to the power of 0.5 t. So in the integral, it becomes integral of 0 to infinity e to the 0.5 t times e to the j omega t and dt. Now if you integrate, this will not converge. Okay, will not converge when t goes to infinity. That's what I want to say that. Okay, for the sake of argument, if you take this guy, then this is a scenario. Okay, so therefore the integration will not converge. The second guy, this guy will not converge. This function will not converge. On the other hand, if you take greater than minus 1, then it will converge. For the same argument, what you do, if you take real of s is greater than minus 1, that means let us say sigma is equal to minus 0.5, because minus 0.5 is greater than minus 1, right? Therefore, integral of 0 to infinity e to the minus t e to the sigma plus j omega, right? So sigma equal to minus 0.5. Let me take this expression straight away. So 0 to infinity e to the minus of 1, let us say sigma equal to minus 0.5 t e to the minus j omega t and dt. Now what happens in this guy? This guy becomes e to the minus of 1 minus 0.5 times t. Now this is e to the minus 0.5 t. When t goes to infinity, then e to the minus 0.5 t goes to 0. Therefore it converges. Okay, so whenever you have more than two region of convergence, you should always choose wisely, so that the whole function, because you are not considering only one function, you are taking sum of two functions here. Okay, one function and another function, two functions. This function individually has one region of convergence and this guy has another region of convergence. But the moment you combine these two functions together, addition of these two functions, then you have to consider the region of convergence such that the Laplace transform exists together. Okay, therefore individually this is a Laplace transform 1 by s plus 2 minus 2 by s plus 1. Then if you rearrange this, this is s minus 1 divided by s plus s squared plus 3s plus 2. Okay, therefore the Laplace transform of 3 times e to the minus 2t u of t minus 2 times e to the minus t u of t. You take Laplace transform, then you will get 3 over s plus 2 minus 2 over s plus 1. Then this is 3s plus 3 minus 2s minus 4 divided by s plus 2 times s plus 1. So 3s minus 2s becomes s minus 1 divided by s square plus 3s plus 2, and this has individually your real of s is greater than minus 2, and this has real of s must be greater than minus 1. So we need to take real of s must be greater than minus 1 together. Individually this is the region of convergence, but if you together if you take, then you have to take minus 1. That means in the region of okay, that we will come to a little later. The region of convergence should not contain any poles. Okay, now let me consider one more example. X of t is equal to e power minus 2t u of t plus e power minus t cos 3t times u of t. Again, you can easily find the Laplace transform for this. So no need to apply the Laplace transform every time. You just split this into in terms of elementary signal, exponential signal, e to the minus t u of t plus this one e to the minus t times 1 by 2 e to the j times 3t 3t plus 1 by 2 e to the minus j times 3t. That's it. So e to the minus 2t u of t plus 1 by 2 e to the minus of 1 minus j3t, okay, plus 1 by 2 e to the minus of 1 plus j3t. Now you can apply the Fourier Laplace transform, or you can directly find the Laplace transform of this guy. Integral of minus infinity to plus infinity e power minus 2t Laplace transform. Okay, this is Laplace transform of x of t is dt plus 1 half minus infinity to plus infinity, then e power minus of 1 minus j3t e power minus st dt plus 1 by 2 integral of minus infinity to plus infinity e to the minus 1 plus j3t times e to the minus st and dt. Now this no need to do the integration again and again. This you directly can write down the result. We know that e power minus 2t e power minus st u of t. What is the Laplace transform for this? 1 divided by s plus 2, and the real part of s must be greater than minus 2. What is the second one? E to the minus of 1 minus j3 times t u of t. If you take Laplace transform, then this is 1 minus j3, okay, plus s. And what is the region of convergence? Real part of s must be greater than this 1 only. Don't need to consider this j terms, imaginary terms, minus 1. And then e power minus of 1 plus j3 times t u of t. If we take a Laplace transform, then this becomes, maybe I'll write down the proper form, s plus 1 minus j3, okay, and this one is s plus 1 plus j3, and again the region of convergence is real of s is greater than minus 1. Now I have 3 region of convergence, and these two are same, real of s greater than minus 1, real of s greater than minus 1. But what about this guy, greater than minus 2? You should choose the one which does not include the other region of convergence, okay, or common area should choose it. Therefore I should choose this one only. If you choose this, then these two guys will not converge. If you choose real of s is greater than minus 2, then these two guys will not converge. okay, for all three Laplace transforms to converge simultaneously. Okay, this also should converge, this also should converge, and this also should converge. We must have real of s must be greater than -1. So consequently, the Laplace transform of x of t is x of s is equal to 1 divided by s plus 2 plus 1 by 2 1 divided by s plus 1 minus j3 plus 1 by 2 times 1 divided by s plus 1 plus j3, and real of s must be greater than -1. Okay, now you combine the terms and make a common denominator. Then after simplification, it is going to be 2s squared plus 5s plus 12 divided by s squared plus 2s plus 10 divided by s plus 2 multiplied by s plus 2 and the region of convergence is greater than -1. Okay. So general rule to find a region of convergence. So we said the inverse Laplace transform x of t is equal to 1 by 2 pi j integral of sigma minus j infinity to sigma plus j infinity x of s e to the st and ds. Okay, and the contour of integration which extends from c minus j infinity to c plus j infinity. Okay, and this is a vertical line. So you are doing the integration along the vertical line from c minus j infinity to c plus j infinity. Okay, and it is a vertical line in the ROC of the Laplace transform. That means what? Your this is your ROC. You choose any point such that the point is C, or let's say this point is C and this point is, let's say, sigma. Therefore, the C value must be greater than your sigma C. Okay, and this is the contour of integration as we mentioned in the last lecture, which is called Bromwich contour. Now, as a result of this, Laplace transformation that we get is usually a rational function. Okay, so the pole and zero locations of x of s completely define x of s except for the multiplying factor. Therefore, x of s will be a rational function. We also note that as long as the coefficients in the two polynomials are real, okay, then any complex pole is accompanied by its conjugate, and any complex zero is accompanied by its conjugate. Therefore, in the complex plane, it is like this. Okay. Also, we said that it is a ratio of rational function, this x of s. It has a numerator polynomial and the denominator polynomial. If you solve the numerator polynomial, you will get zeros, and if you solve the denominator polynomial, you will get poles. And the poles are denoted by this cross, and the zeros are denoted by circle, small circle, like this. Therefore, the general format of your x of s is going to be some constant times m times numerator polynomial and the denominator polynomial. That means what? M times the numerator polynomial can be factorized as s minus z1 times s minus z2 and so on and so forth up to s minus zm, m number of zeros. In the denominator you have s minus p1, s minus p2 up to s minus pn. And as I said, a rational function means the ratio of two polynomials, numerator polynomial and the denominator polynomial. Okay, and these two polynomials could be put in this form. Okay, the numerator is factorized as s minus z1 times s minus z2 times and so on and so forth, and the denominator is likewise factorized as s minus p1 times s minus p2 and so on and so forth. Okay, then the Laplace transformation x of s is defined by the values z1, z2 up to zn, p1, p2 up to pn, apart from the constant m, multiplying factor. This m is the multiplying factor. Therefore, this x of s can be represented in the complex plane like this. Okay, by the location of x of s and the poles of x of s. So, zeros are normally marked by means of a small circle and poles are marked by crosses. So, the pole and the zero locations are marked in the S plane, and this one is called a S plane. We know that S is equal to sigma plus j omega, this one is sigma axis and this one is j omega axis. So, the pole and the zero locations of x of s completely define the x of s except for the multiplying factor. If somebody comes and gives you these are my pole locations and these are my zero locations, then you can easily find out what is your x of s, because this is p1, p1 conjugate, z1, z1 conjugate, let us say this is z2. You can easily find out the relation s minus z1, then s minus z1 conjugate, then s minus z2 in the numerator. In the denominator you put one more poles like this. Let us say this is p2, p2 star, p3 like this. So, you can put all those things, s minus p1, s minus p1 star, s minus p2, s minus p2 star times s minus p3, except that we do not know what is the value of m here, okay, that we need to find out. So, rest of the polynomial you can find it very easily, but you cannot find out that m value. And we also note that as long as the coefficients in the two polynomials, so in the numerator polynomial and in the denominator polynomial, the coefficients are real, then any complex pole is accompanied by its conjugate. Suppose that you can recall from your quadratic equation ax squared plus bx plus c, then this x has minus b plus or minus square root of b squared minus 4ac divided by 2a, and this root is complex conjugate if and only if a is real, b must be real and c must be real, then this root will be complex conjugate pair. Okay. So, therefore, the complex 0 is accompanied by its conjugate, complex pole is accompanied by its conjugate. Okay. And the abscissa of convergence is sigma c. The abscissa of convergence is larger than the maximum value of real part of pi. See, I have p1, p2, p3 like that. Then how do you find out the real part of s must be greater than maximum value of this real part of pi. So, whatever the pi you are having, that will define the abscissa of convergence. Okay, that the ROC starts from the abscissa of See, ROC starts from the rightmost pole. So when you plot the poles, the ROC starts from the rightmost pole. That means the ROC does not contain any pole. Even if you take this example, by the same 1 minute, let me finish this diagram. Where is it? Yeah, where I is equal to 1, 2, 3 and so on and so forth. So that's how you find out the region of convergence if you have more than one pole. If you take the previous example, the last example, you have 3 poles here, right? This is first pole, second pole and third pole. Fortunately, these two are complex conjugate poles. So in that case, what is the P1? P1 is equal to minus 2. P2 is equal to minus 1 plus J3 and P2 conjugate is equal to minus 1 minus J3. Now out of this, which is greater? Sigma C must be greater than or equal to real part of Pi, where I is equal to 1, 2 and 3. Okay, now this is minus 2. No, I forgot put to maximum of this. Maximum of real part of Pi, like this, where I is equal to 1, 2 and so on and so forth. If you substitute 1, then you will get a sigma C is greater than minus 2 and then sigma C is greater than minus 1. Out of these two guys, which is maximum? Minus 1 is the maximum value. Therefore, sigma C is the greater than minus 1. This is your region of convergence. So that's what we put here. So the maximum value of the real part of the poles defines the ROC. And we have seen this in the case of simple functions like a unit step function and so on. So where if you take e to the 2t u of t, then sigma c is greater than or equal to minus 2 and so on and so forth. Okay. Now finally, I would like to make some comments on notation. As I mentioned, the Laplace transform exists only for 0 to infinity for unilateral Laplace transform. Okay, so this is for unilateral Laplace transform x of t e to the minus st and dt. Okay, that means what? X of t is equal to 0 for t less than 0. I am considering a causal signal. If you take an bilateral Laplace transform, this is unilateral Laplace transform. If you take bilateral Laplace transform, then x of s is equal to integral of minus infinity to plus infinity x of t e to the minus st dt, where x of t not necessarily 0 for t less than 0. Okay. Now one more thing, important note I want to make it here. Suppose I want to make the Laplace transform of a constant function, then what is its Laplace transform? Again, by definition, constant k exists, let us say for all values of time greater than 0. So in this case, what will happen? 0 to infinity k times x of t is k, some constant, k times, let me define properly. I have a signal x of t which is k for t greater than 0 and 0 for t less than 0. That is a causal signal. That means what? It is again a step function. It is 0 and suddenly jumps by a k unit. Okay. So, but in the context of Laplace transform, we assume that the value k starts from 0 minus. because we can treat only functions which are 0 for negative values of time in the Laplace transform domain. Therefore, you put k and 0 minus to infinity e to the minus st and dt, then finally you will end up with the k times s, where real of s is greater than 0 if you work out on this. So, likewise you can find out the Fourier transform of some other signals also. So, let me stop at this point. In the next lecture we will talk about properties of the Laplace transform and followed by the region of convergence for Laplace transforms. In fact, we will start with the region of convergence first and then we will move on to properties of the Laplace transform. Let me stop at this point. Thank you very much.